exponential growth. Modeling exponential growth. What is exponential growth? Let's take a look at an example. Bacteria. A type of bacteria grows so that it triples in number every day. On the day that the counting of the bacteria began, there were 100 already established bacteria. This means that the population of the sample is 100. Now, the question is to find the population after the 4th day of observing the bacteria. To do this, let's create a table of values. We will create 3 columns, 3 rows. The first column will be the number of the day, the second will be the population, and the third will be any notes that we need to look at or take into consideration. So, for the population, we begin with 100 and we know that it triples by 3 at the end of the day. So, if we look at day 1, we know that 100 bacteria times 3 would equal 300. So on day 1, we see that the initial population has tripled from 100 to 300. Now, on day 2, we started out on day 2 with 300 from day 1. That number tripled, so we know at the end of the day that we have 900 bacteria. If we continue the pattern, we will notice that on day 3, 900 times 3 would give us 2,700 bacteria, and on day 4, 2,700 times 3 would give us 8,100 bacteria. Wow, they're really growing. This means that on day 4, if you started with 100 bacteria on day 0, you would have 8,100 bacteria by day 4. Now, the second thing we want to take a look at is how to write an equation to model this growth. The equation would explain the relationship between the day and the population. To do this, express each population in number 1 in terms of the number of times the initial population is tripled. To do this, we will take our table of values and we will set our initial value to be 100 and we will multiply it by 3 because we are tripling, but we will include the exponent value to represent the day. So for day 1, we will start with 100 bacteria times 3 to the exponent 1. And this will give us the same answer we found in number 1, 300. If we continue this pattern, for day 2, 100 times 3 to the exponent 2 would be 900. For day 3, 100 times 3 to the exponent 3 is 2,700. Day 4, 100 times 3 to the exponent 4 is 8,100. We get the same values. We can then take this expression or this relationship between the day and the population to create a formula. So on day n, which could represent any day in our sequence, the population would be 100 times 3 to the exponent n. After n days, the initial population has tripled n times. An equation relating the population P to the number of days n is therefore P at n is equal to 100 times 3 to the exponent n. 100 represented the initial population. 3 is from the fact that the population tripled, and n is the time on which we want to determine the sample size of the population. Now we want to graph the relation. From the graph and the data, we want to determine, is this a function? Why or why not? Where do we start? Let's start by using the values found in the table of value. Then, plot these points on an XY Cartesian plane. Here is the values in a table of values. The day, 0, 1, 2, 3, 4, and the total population, 100, 300, 900, 2700, and 8100. So we will start by drawing on graph paper the x-axis and the y-axis. The x-axis will be 2, 4, 6, 8, and so on up to the value of n. And along the y-axis we'll go up by 900 to 1800, 3600, 5400, 2700, and 9000. The equation, of course, we've determined to be the population for n, which is equal to the initial value of 100 times the base 3 to the exponent n. So we want to first plot 0 and 100, 1 and 300, 2 and 900. Now you'll notice it starts to curve as we plot 3 and 2700, and wow, it's gone up very fast at 4 and 8100. This is the shape of an exponential growth function. Now, is it a function? Let's use the vertical line test. If we draw a straight vertical line and it passes through the graph only once, then the graph represents a function. Since we've done the vertical line test, it passes through one point, we call this a function. Another way of being able to do is by using the domain and range test. If for every value in the domain, which is of course the x values, there is a unique range value, so it's a one-to-one mapping, the relation is a function. This relation represents a function. Now, number 4, assuming this trend continues, predict the population after 1 week, which is 7 days, 2 weeks, which is 14 days. This could be done in 2 ways. By finding the values from the graph, substituting the required dates into the formula for the value of n. Assuming this trend would continue, we could predict the population from the graph, but since the graph increases steeply as n increases, it is very difficult to extrapolate these values. A better approach is to use the formula and substitute the 2 required day values into the equation. The given equation is P at n equals 100 times 3 to the exponent n. At 1 week, which is 7 days, this would become P at 7 would equal 100 times 3 at 7. We replace the n by the numeric value 7. From there, we solve equals 100 times 2187, which would be 218700. After 1 week, the bacteria population will be 218,700. The given equation is P at n equals 100 times 3 to the exponent n, and we want to find the value now for 2 weeks, which is 14 days. This would become P at 14 equals 100 times 3 to the exponent 14. Again, replacing the value 14 for n, which would equal 100 times 4,782,969, which gives us the huge number of bacteria, 478,296,900. So after 2 weeks, the bacteria population will be 478,296,900 bacteria. Exponential growth, then, is a pattern of growth where each term is multiplied by a constant amount, which is greater than 1, to produce the next term. This produces a graph that increases at a constantly increasing rate from a common ratio. In our example, this common ratio is 3, which you might notice is the base of the exponential value in the equation. Let's grow some skills.